So my name is Tomasz Bednarz. I'm the conference chair of SIGGRAPH Asia 2019 that will be held in Brisbane in Australia. So I strongly encourage you to come to SIGGRAPH Asia this year, especially if you like Demoscene, because for the very first time ever, Demoscene program will be melted within the SIGGRAPH program. So we have official program. You can bring your Commodore C64, Amiga 500, if you have ZX Spectrum, and you can do your demonstrations, and maybe you can win competition. I don't want to talk too much because we're going to focus purely on Demoscene this year. So give the mic to John, who is leading our Demoscene program.
Awesome. Thank you, Thomas. Wow, what a turnout. Fantastic. We do have a couple of surprises for you. First of all, my name's John Doolan, and I'm lead programmer at a company called Virtual Immersive. We're based in Sydney. So I'm a computer graphics nerd that does augmented reality and virtual reality. I'm a long-time Demoscener, so since the late 1980s. I started out as a teenager in the Commodore 64 scene, so I'm a retro guy. I love it. But I also love new school productions. Can I get a show of hands who's participated in the Demoscene before? Okay, that's a good number. And who's heard of the Demoscene but haven't participated? Whoa, all right, we're going to fix that. And is there a show of hands for people who haven't even heard of the Demoscene? We've got a couple. Okay, look, I'll do a very super quick introduction about what the Demoscene is. Essentially, it's a subculture of digital art, music, and code. It's been around for about 40 years, around about the same length of time as the retro computer scene, so the Commodore 64 era, Amstrad, Spectrum. It's held together by Demosceners, these crazy crew, that create real-time demos, real-time productions, and they compete against one another at demo parties. It has a strong foundation in the retro computing world, as I mentioned, but current technology is often pushed to its limits in the new school category as well. So how is the Demoscene related to SIGGRAPH? So before I started working in industry as a graphics programmer, I found a passion for computer graphics in the Demoscene. And Dr. Tomasz Bednarz here, for example, who's currently chairing the SIGGRAPH Asia 2019 conference in Brisbane, Australia, also fell in love with the Demoscene in Poland. Yeah. So a lot of professionals got their start playing around with graphics technology in the Demoscene. So the last few years here at SIGGRAPH, Thomas has organised similar birds of a feather sessions such as this, and they've always been extremely popular, as we've got here today, standing room only. So I'm excited to announce that for the first time ever, the Demoscene has been included as an official program at SIGGRAPH. So this is the first time it's been an official program. It's always been sort of done as a birds of a feather session, but this time round we'll have a real live demo party at the event.
Because you have crazy chair?
Because we've got a loony chair, that's me. So I'm running this event. There'll be beers, there'll be demos, there'll be compos. It's a Demoscene party, so come on down. We'll have a retro museum as well, so for those of you who would like to get their hands dusty and brush off some Commodore 64, Amiga, old school computers, it's a hands-on interactive retro museum, so come and check it out. Okay, a couple of surprises. So we have an invite that we did on the PC, so I'll just quickly show that now. It was done in C++ and OpenGL.
Maybe before you say what is invite.
Say what it is?
What it is, yeah, invitro.
Okay, so an invitro, for those who don't know, is a demo created by Demosceners to invite people to Demoscene events. So we've created a demo, an invitro to show to you guys today. The code and art were done by the Australian Demoscene, and music was done by Super Gloom here of XS. All right, I'll kick this off. It may need to. Yeah. No, I got this.
That's copyrighted me.
Let me just turn off duplicate displays. I mean, turn on duplicate displays. Okay. Wish me luck. Oh, it's on this screen. highly trained professionals, everyone. Stay calm. We got this. I need to duplicate and accept. All right.
One more time.
And again, round of applause. Yeah, yeah.
I say this is very first time ever.
Dim
Lights, please. Short and sweet. I have another surprise for you. This, by the way, that's the first time this has been shown, so it's officially released invite now, so it'll go up on all the appropriate Demoscene websites. And we've actually got another surprise for you. A colleague of mine in Sydney created a Commodore 64 invite for us to watch as well, so let's enjoy that. Yeah! Oh dear.
And like all C64 demos, they never end.
And it's not possible to kill it
I
now.
can't even,
Just switch it off.
How do you spell Alt F4? No, that's not even working.
The power button.
Yeah.
Cool.
Wow. All right, so a round of applause for Ziggy and for Alex for helping out with the music. Yes, that worked correctly. So that's all I have today, but come on down to SIGGRAPH Asia in Brisbane, sunny Australia. We'd love to have you there. There'll be much more information posted about the Demoscene event as we know more, and these invites will both be available online, so check them out. Might hand off to Bent. Thank you. Thanks, mate. Oops. Oh.
Oh, Jesus. Well, now you can see me. Let me just quickly check that sound works, because it didn't earlier. I have to unplug and plug it back in. Now it works. All right. I've been asked to help organize this. My name is Bent. I'm part of the Scene.org, the international scene organization. And after, I think, 7 or 8 years of helping out SIGGRAPH, I've joined the International Resource Committee of SIGGRAPH this year. So that's also fun, I guess. I'm doing booth duty tomorrow, which I was told yesterday, so that's going to be fun. Come on and ask all your questions. I can answer them all. But I've been asked to help out because I'm a Demoscene party organizer in Europe. And I know a few people who do Demoscene stuff. Eric, on the far my left there, is going to be in the dark. Well, he is in the dark. He is going to be talking last. But first, I want to introduce Matt Svoboda, who is opening his laptop so you can actually see his face. But first we do that. So both of these fine gentlemen have created a whole range of demos from the Amiga C64. I don't think Matt actually worked on the C64, did you? No. So he didn't. The other the guys did. They're cooler. Matt is just a child, as you can see. But they all created the demos. So I've selected one demo from each. So we're going to show that as an intro, and then they're going to do their presentations. And this sounds incredibly self-serving, but I also made the music for both of those things. So if there are any more musicians in the demo scene, there are tons of gigs to go around, so I can't make all of that stuff. But I think we would start I'm going to start by plugging in this HDMI cable. The suspense. That helps. And we're going to start by showing a demo called Number One, Another One, from Fairlight and the CNCD, which will hopefully have audio. And if it doesn't have audio, I'll stop it and start it again. Feel free to hum or sing or whistle, whatever your preference is for loading music.
So this demo won
There we go. That's a proper. Yeah, this demo won the pretty prestigious assembly demo party in Helsinki, Finland last summer. And we haven't made anything since, so maybe it's time. I mean, all that rambling, and we still haven't loaded all of it. Isn't it interesting? How are you guys doing? It's gonna get warm in here. I can feel it. They close the doors, so. Come on. Come on.
Yo, hey, welcome to the East of my G. Ain't nobody better than M.E. Go by the name of the ultimate sound. Better watch your back when you step in my town. Okay, respect that shit. That roll up on your block and rep that shit. That's I'm the only dude that can do it non-stop. What? And you the dude that always go and run and call the cops. Check it. My shit. Check it.
Pretty cool. So the last handle there was Smash. That's Matt. We didn't go into this earlier, but in the demo scene, everybody picks like a lame thing to call themselves because that's really cool. And we did it in the 70s, barely, and in the 80s, and we're still doing it. So he was the lead programmer of that thing. Everything you just saw was real-time rendered on this laptop in this case. If you have a really beefy computer, you can run it in 4K. I dare you. I'm just going to hand it over to Matt, who's going to do the first sort of techie, talky part of this little session of ours. And then I'll come back and play a demo Eric made before his talk. So if you could all give Matt Swoboda a big applause, that would be good.
Hello. Can you hear me okay? So my name's Matt, and I'm professionally, I work for a company called Notch, which is, funnily enough, a company focusing on using techniques in real-time graphics for making things like motion graphics, using real-time as a workflow for making content. But in the demo scene, my name is, my super cool handle that I chose in the 90s is Smash, and I'm in the demo group Fairlight. So when Bent told me I was talking a couple of days ago, I decided to kind of go a little bit off-piste and talk about pre-calc. So demos from the beginning of time have always focused on trying to look super amazing and cool and do things that are impossible to be done in real time on a computer, or at least appear that way. And they primarily achieve this by cheating massively. Through a number of ways, often just plain faking and lying about what they're doing, but in particular, using pre-calc and animation to achieve things that would be impossible to do real time, and then lie and say they're really doing them in real time. So there are two different things. Pre-calc focuses on generating data up front, or generating information that can be reused up front. And animation typically refers to just streaming in from disk or from memory whole frames of stuff. So I'll give some examples. This is the famous kind of slightly tenuous example, but one of the very first kind of early Amiga sort of things done on the Amiga is this, the Juggler. It's pure ray traced flick animation. His classic State of the Art by Spaceballs, a very famous Amiga demo from 1992. All vector animations, pre-calcs and shown up front. The famous the famous 242 by Virtual Dreams of Fairlight, a very famous demo. Virtually entirely video and streamed in, played back frame by frame. And now we get to the real pinnacle of cheating and faking. Starstruck by TBL on the Amiga 060 in 2007. Amazing 3D content, impossible on Amiga. It's basically all animated skyboxes streamed in. So most of the 3D visible there is a big animated skybox, and then the little 3D robot there in the middle is actually polygons. Although I'm sure they pre-calc those as well. PC is not immune from such faking. This is Real-Time Radiosity 2 by Bronx. It's not real-time radiosity at all. It's all pre-calced. So both lying and pre-calcing in one simple and effective delivery. But in general, PC demos these days don't really do that anymore. They're all very boring and real. So I'm using personal examples because I had screenshots to hand. But for example, NumRes by us in 2011 PC demo, millions of particles, very heavy effects. Yeah, it was all done for real. There was no pre-calc. It was all actually done in real time. Wonder, also by us, released last year. Some really nice global illumination techniques and so on. And fluid dynamics, some kinds of things. Again, actually done for real, not pre-calced. And then number one, you've just seen some big physics effects and various things throughout the demo. Again, no pre-calc, it was all actually done for real. Very, very boring and realistic. So why is this done? Why aren't we pre-calcing and faking and cheating everything anymore? I think the reason is that it's actually really hard to do that. These days, when you're dealing with a very high resolution target and the fidelity requirements are very high, to make pre-calc data to satisfy that, the data ends up being very large and very hard and often too big to fit inside a demo which typically has a size limit of around 200 megs. And then to actually work with pre-calc data is hard. Like, it's hard to deal with. You have to make the data, play the data back, edit it. When you edit it, you have to go back and remake the data. It's incredibly annoying. And the reality is that a lot of stuff just isn't worth pre-calcing anymore. GPUs are fast enough that you can do a lot of stuff for real. So it's easier, and easy is good because we're all lazy and working on limited time, so we end up doing what is easy. So the easier thing is just to do stuff you can do for real and not bother with that whole being impossible business. I want to end this debacle. Let's make demos great again by faking more. But doing this with a modern, updated twist. So what we need to do is we need to find things now that are incredibly hard to do and slow and difficult to do in real time, and pre-calc them, and then lie and say we did them in real time. So I'm going to give some actual some examples of real-world stuff we're doing now to explore this noble cause. So the first example, so what we need to do is we need to actually find something very slow to calculate in real time and develop a clever way to kind of pre-calc it, store it, and then find ways to reuse that data so you can turn like 5 seconds of content into like 30 or 60 seconds of interesting. Easier said than done. But here's an example. So fluid simulation compression. So this is a fluid solver in Notch. So it's working on a 512 cubed grid, using a full Navier-Stokes simulation with lots of iterations, so it looks nice. So it's a very large simulation. You get about 2 gig of data per frame, and it takes about one second a frame to simulate. So it's pretty slow and heavy, but it does look cool. So what we need to do is we need to find a way to pre-calc that. So what we did was we developed a compression codec for fluids, for the fluid solve. So you exploit things like empty areas, gradual changes, and you use motion vectors from the simulation to reuse previous frames data. And with careful compression and so on, we were able to make a codec that does about 4 megs a frame for that 512 cubed cache, which is just about viable if you only use about 3 seconds of it. But then you can reuse that data in many clever ways, and we can light it all in real time, slow it down, rewind it, and so on, to stretch that content, not just to 10 seconds or 20, but probably to a good 2 minutes, if we really try. This example, so this is the same data cached out, and then we're relighting it, reusing it different ways. We can reorientate it, we can slow it down. We've got our motion vector data potentially to stretch it out. And we can make, through clever use of pre-calc, we can start to make some stuff that would never really be possible in real time. And then we can tell everyone that it was real time. And everyone will believe us. This is the culmination of years and years of work of actually doing stuff for real. So when we start faking things, people don't think it's fake. There's a lot of investment in this. So yeah, I'm encouraging everyone to do this. Do the impossible by cheating. There's a key technical point though here. It's not easy to do this. Firstly, you have to control the whole pipeline. Like in order to generate the right kind of data to be able to pre-calc, to be able to reuse, you need smart ways of generating that data. So, for example, we've developed our own fluid solvers. We've developed our own ray tracer, so we can control the entire path traced pipeline. So we can choose what elements we cache out and what elements we pre-calc. So we're not just stuck with a video or the end result. We're able to pre-calc certain parts of the pipeline and do certain parts for real time. And then develop your own codecs and techniques to compress that data. By doing this, we can truly make demos great again by faking. Thank you very much.
An inspiration to us all. All right, so now coming up is Erik Feilund, as we say in Norwegian. Any Scandinavians in the house? Yeah. One. Fair enough. Before he comes on to talk about something completely different, we're going to show this demo that we did a couple of years ago. And we press the Go Gadget Go button.
Here we go. Premeditation constantly going on in my brain. I will stack my grain and count my bread. Hopefully I stock a lot and now bread before I'm dead. Hustle hard in the sun, then recline when it rains. I'll be chilling in my house, my wife giving me brains. Education every day, boy I'm married to the game. Get a map if you lost, ain't no pen without gain. I told the price, I'm all about a function of the fame. I'm in a rush to spit a verse, package it and get some change. In a rush to do a show overseas and get some fame. I'm doing well, don't matter if you think that I'm insane. In the summer make it rain, cause my fat at on the bank. Point reason every day, nigga find your own name. And the business, it's a shame if you ain't got a name. Could you go in the rain with no umbrella in your hand? There comes a time the people just buy you for your name.
All right. So for the novices in the audience, the reason we keep writing all these words is that we're basically greeting all the groups that we know. And this was the 20th year anniversary of the forming our group. So we decided to just go back and look at all old demos and credit everybody or greet everybody that we ever greeted through the 90s. So this was fun.
All right. Yeah, so I will be talking about creative programming and the brave new world of explicit APIs. So first of all, I'm Eric, or Kusma, as I'm called in the demo scene. I'm a graphics programmer, and I've been working professionally with that for a long time. Working mostly on OpenGL and Vulkan-related stuff. I work for Collabora as a principal software engineer, and there I work mostly on Mesa and OpenGL-based technologies. Yeah, and in the demo scene, I'm a member of the access group, which you just saw a demo of. So first of all, for those who don't do much low-level programming, I will talk a little bit about what explicit APIs are. So they are the new generation of very low-level, close to the metal APIs. Microsoft, Kronos, and Apple has all released their APIs. For those who don't know, Kronos is the standardization organ behind OpenGL. So the DirectX 12 and Metal are proprietary for Apple operating systems and Microsoft operating systems, and Vulkan is cross-platform. I will be focusing on Vulkan myself because that's what I have the most background in. So some of the terms I will be talking about are Vulkan specific, but most of the things I will talk about applies to the other APIs in one way or another as well. These explicit APIs, they move a lot of the difficult to deal with problems from the drivers to the applications. With the assumption that the application knows more about what it's going to do and how it's going to use data, so it can probably do a better job at it, but it makes it tricky to write the applications. You get much more serious bugs when you do something wrong. So typical things that you have to deal with yourself is memory management. It's GPU to CPU and GPU to GPU synchronization. So like making sure that a DMA copy is finished before you use the memory, for instance. You have to deal with what's called pipelines and descriptor sets. I will come quickly back to that a little bit later. And kind of the most, I think, tricky thing is the image barriers, which I will also go through in more detail. Yeah, so the pipelines, they're an encapsulation of all of the rendering state that's needed, or well, almost all that are needed in order to render something. They're like shaders, blend states, rasterizer state, these kinds of things. But they also include something not quite obvious to everyone, and that is things like frame buffer formats. So they're not a direct reflection of the material you're using. They're also kind of the properties of an object together with the environment it's going to be rendered in. They are relatively costly to create, so kind of creating them as you need them is not the greatest idea. There's some some tricks you can do to speed up some things, like you can create some base pipelines and make some derivative pipelines from that, but it doesn't really solve the problem. You need to kind of create stuff up front, like at load time and things like that. Otherwise, you risk getting frame rate hitches here and there. Yeah, and to use these, you bind them to a command buffer. I should probably mention that these APIs are all command buffer oriented, so you kind of fill the GPU buffer with commands for what to do and execute them. And they, yeah, when they're API or command buffer oriented, kind of state doesn't leak across command buffer. So you kind of bind something to a command buffer, and the next command buffer is going to know nothing about that, and you're not going to be able to reuse the binding. Descriptor sets are the rest of the rendering state. They are bindings between resources, typically memory on the GPU, and the pipelines. So that includes things like texture images, samplers, yeah, uniform buffer objects, yeah, inputs like vertex data, things like that. They are addressed by a descriptor set and a binding, and they're similar to pipelines in that they're bound to a command buffer to use them. Yeah, and then image barriers. So images on modern GPUs can be in one of multiple states at the same time. These states are based on what kind of usage like what the purpose of using them for is. Typically, like if you're gonna have a render like rasterize things into it, so a frame buffer attachment, it can be shader like marked for reading from shaders and yeah, DMA modes and stuff like that. These states need to be transitioned explicitly between by the applications, and the transitions needs to happen as early as possible, but also as few times as possible, which is not entirely obvious how to do. A typical transition is frame buffer decompression. A GPU can often store frame buffer data when you're rendering to it in a more memory efficient, like in a compressed format. So it uses less memory, but not all GPUs are able to, for instance, sample textures out of that format, so they might have to be decompressed into memory first. Some transitions are no-ops on some GPUs, and it's really hard to know. Like you don't really know which are allowed and which aren't. So you have to kind of be by the book. You have to do the tricky work. Traditional APIs, so OpenGL and DirectX 11 and before, they do the transitions for you. The APIs, the drivers there, they have a lot of heuristics to kind of figure out when to do transitions. These heuristics can utilize hardware-specific knowledge to a much bigger degree than you can as a Vulkan or something like that developer. And they can even target specific applications. They can look at, you're running this particular AAA game, so whenever you've done this amount of draw calls, we know that you're gonna do something else. This is hard to beat with generic solutions. So if you're kind of trying to do it lazily, like look at what your application is doing and kind of do this, you're probably gonna lose. You're not gonna beat the driver. So to do efficiently, to do these image barriers, you kind of need to have a time machine. Because you're building up a frame in terms of operations, and you want to insert the barrier as early as possible before the image changes purpose, which it's something you can notice pretty late. You typically notice that when you use it for a new purpose. So in order to solve this, there is a common approach called a frame graph. This is a data structure where you record a full frame of rendering into it with dependency tracking between the different operations. You traverse the graph and you place the barriers algorithmically. This is a pretty good choice for a data-driven engine where you already need to process your data in a structured way anyway, the scene data. But it might not be such a good choice for a kind of more of a code-driven engine where you prototype things and stuff like that, where you kind of need to change all of the details of the engine often. Frame graphs also solve some other problems, but they are kind of out of scope here. Those problems generally have other solutions as well that aren't very complicated, I would say. Yeah, so when I'm talking about creative programming, I'm thinking of a specific kind of subproblem of creative programming. So my definition is when you write applications that target a very specific type of rendering. Code-driven, not data-driven. So this means that the programmer is the creative person who sits down and kind of writes a special purpose renderer for something. These tends to be less kind of engine-heavy ways of programming, and more framework, or kind of like having a playground, kind of take some code and modify it and like play around with it. This gives more control to the programmer, and yeah, so kind of that's where the creative kind of part of this comes into it. There's other totally valid ways of defining what creative programming is. This is for this talk. This is my definition. For this purpose, you typically don't see so much kind of scene graph stuff, but more open-coded kind of logic to draw things. Yeah, and that comes from the simple fact that as a programmer, defining your scene in terms of code is kind of the most logic way of doing it. It's the most straightforward and to the point way. So the kind of the goal that I want to do when I do creative programming, or I want to build a system where we can be very specific in defining our rendering, but without kind of repeating tedious code too much. My approaches are usually to write kind of a new renderer per project. And that's just kind of like a for loop through some objects, applying some shaders with a little bit of, you know.
Why don't you tell them what your previous engines were called?
Well, so I made one engine called Last Engine Ever, and then I made the sequel to that called Very Last Engine Ever, and my current engine is called Even Laster Engine. So, you know. Yeah, and yeah, for that kind of way of programming, things like scene graphs and kind of setting up, yeah, a lot of abstraction and stuff tends to get in the way rather than help you. Yeah. So then, of course, the obvious question is why do you need to do both of these things at the same time? Explicit APIs and creative programming. You can, you know, maybe stay with the old ones. Well, or you can use a pre-made engine, for instance. That's also a perfectly valid option.
Shader, for example, I'm guessing is pretty popular as well.
Yeah, there's also these guys here who make this thing called Notch. Yeah, so for me, it comes down to a couple of reasons. It comes down to control. I want to make these very specialized renderers, and that just then tends to not work very well into big kind of pre-made engines. And second of all is that I want to like build a code base that I can use for years and years forward, and I don't want to stick with something that might not stay around. And the old non-explicit APIs are sadly kind of fading away slowly. So for those who don't know, like with DirectX, it's pretty obvious. You see the number in the end, and the latest one is explicit, and the other ones aren't. That's probably going to stay that way for the next version also. For OpenGL, it's the rate of new specifications coming out has slowed down very drastically, to put it mildly. And the only specification of OpenGL that was released since Vulkan was released, 4.6, was mostly released just to bring up Vulkan compatibility. So it's not entirely true, and like OpenGL isn't dead or anything like that, but it's not moving as fast as it did. Yeah, and then also it's just a simple, like, this is fun kind of argument where I'm doing this on my spare time. I work as a graphics programmer. It's a good opportunity to play around with some new technology. So, you know. Yeah, so I want to talk about this image barrier problem because as I said, I don't want to encapsulate the rendering too much, but I also want efficient barriers. One approach I've used already is to just manually place the barriers by code. This is what we did for a demo called Aurora. It was not pleasant. I'm not doing that again. That was just too much trial and error and stuff that went wrong. So I need something automatic, but I also don't want it to kind of get in the way too much. So I need to like observe the needs for barriers and kind of figure out why do I when do I need to do this? There's some things that don't really need any active barrier management. All the texture data, all the textures you load from a file and you never modify, they can just stay in the read from shader state. So effectively, the only thing that you very actively maintain are render targets, or render textures. So when you render to a texture and then you texture from it later on. So maybe we can do like this, something a little bit similar to a frame graph, but that only solves the render target problem. So here's my kind of proposed alternative. So yeah, these are only the automatic state transitions. I only want to solve this for renderable textures. And really, the only thing we need to know after the fact is kind of when to transition out of the renderable state and when to transition back into it. So that is typically, we need to transition right after the last write happened and right after the last read happened. Those are kind of the point that you want to do something. If I separate all like rendering to each render target into its own command buffer, I kind of get a time machine, because I can append to one of the command buffers while I'm building the next one. And you can submit all of them in one go. You can submit a bunch of command buffers together. So if we keep track of the last command buffer that read and wrote to a renderable texture within a frame, we can just patch up the command buffer, add one command to the end of it, and everything should be okay. So yeah, that's pretty much it. Yeah, thank you.
All right. I think we're, some of you are probably eager to get to the thing that's already full, so don't even bother, but you can try. The fast forward stuff is probably really packed, but it's supposed to be really fun. I wanted to just close out, say, turn off the lights, and then say from from Thomas and Johnny and myself, thank you for coming. We were going to put out a slide where you can find more demos. I think, whoa, that's bright. you can follow me on Twitter, and I'll post whatever we shown and like a whole about other stuff. And we have our blogspot for the Demoscene BOF as well, and we'll put up a list, like tons of demos. But yeah, run to the fast forward thing. You probably want to do. And come to Australia. There are several things he wants to kill you. None of them are at SIGGRAPH.